Let's look at triple integrals in spherical coordinates. We've used triple integrals to find the mass or center of mass of a solid. Mass m of a solid t, here's a cool example of what could be a solid t, is the triple integral over t of delta of xyz dz dy dx, where delta of xyz is the density of the solid at the point xyz. We saw when we worked with double integrals that sometimes we need to convert a double integral from rectangular to polar coordinates in order to evaluate it. Similarly, we sometimes need to convert a triple integral from rectangular to cylindrical or spherical coordinates in order to evaluate it. Let's say, for example, we're evaluating the integral from -2 to 2, negative root 4 minus x squared to root 4 minus x squared, 0 to root 4 minus x squared minus y squared, z squared, square root of x squared plus y squared plus z squared, dz dy dx by switching to spherical coordinates. That's a mouthful. Okay, when we switched a triple integral from rectangular coordinates to spherical coordinates, dz dy dx became r dz dr d theta. When we switch a triple integral from rectangular coordinates to spherical coordinates, dz dy dx becomes rho squared sine phi d rho d theta d phi. In the same way that I didn't really explain where the r came from, I'm not really going to explain where the rho squared sine phi comes from. It's just what happens when we make the substitution. Okay, so the triple integral of f dz dy dx becomes a triple integral of f rho squared sine phi d rho d theta d phi. Now let's change the integrand f. We use the same equations as before to convert the integrand f from rectangular to spherical coordinates. Here they are. X equals rho sine phi cosine theta. We saw these earlier. Y equals rho sine phi sine theta. Z equals rho cosine phi. And this one really comes in handy. X squared plus y squared plus z squared equals rho squared. Thus, f of xy, which is z squared times the square root of x squared plus y squared plus z squared, this was the integrand, the function we were integrating, becomes this, because z equals rho cosine phi, so z squared is this, and what I'm circling here, the square root of stuff, that's just plain rho. Okay, so the integral of z squared, square root of x squared plus y squared plus z squared dz dy dx becomes rho cosine phi squared rho. That's where the integrand comes in. And rho squared sine phi d rho d theta d phi. That's what dz dy dx becomes. So when you multiply all of this out, you end up with rho to the fifth cosine squared phi sine phi d rho d theta d phi, a triple integral. Now let's find the new limits of integration by looking at the solid we're integrating over. Z goes from 0 to the square root of 4 minus x squared minus y squared. Well, what is this solid? Z equals the square root of 4 minus x squared minus y squared. Z squared equals 4 minus x squared minus y squared when we square both sides. Oh, that's just x squared plus y squared plus z squared equals 4. We know what that is. That's a circle of radius 2. Thus, z equals the square root of 4 minus x squared minus y squared is the upper half of a sphere of radius 2 centered at the origin. Z equals negative square root, that would have been the lower half. Because z goes from 0 to the square root of 4 minus x squared minus y squared, we're integrating over the upper half of the sphere. Again, the lower half would be negative square root of 4 minus x squared minus y squared. Theta goes from 0 to 2 pi, it's a complete circle, and phi goes from 0 to pi over 2, so we get the entire hemisphere. Okay, see, theta goes from 0 to 2 pi, so we're going all the way around, and phi is this angle, the angle between the positive z-axis and the line segment connecting the origin and the point. And so since phi is going from 0 to pi over 2, we get the entire hemisphere. Okay, so this is our triple integral. 0 to pi over 2, 0 to 2 pi, 0 to 2, rho to the fifth cosine squared phi sine phi d rho d theta d phi. Let's integrate this with respect to rho. We get rho to the sixth over 6 cosine squared phi sine phi as rho goes from 0 to 2. Plug in rho equals 2, we end up with this, because 2 to the 6th is 64. Plug in rho equals 0 and we get this. Okay, so let's simplify this a little bit. 64 sixths, that's 32 thirds. So we've got 32 thirds cosine squared phi sine phi. That's our new integrand. Let's integrate this with respect to theta. So we get 32 thirds, you get the integral from 0 to pi over 2, 32 thirds cosine squared phi sine phi theta, as theta goes from 0 to pi. That should be an equal sign. Let's see, plug in theta equals 2 pi, and we end up with this. Plug in theta equals 0, we get nothing. So we end up with the integral from 0 to pi over 2 of 64 pi over 3 cosine squared phi sine phi d phi. Use substitution. We're going to let u equal cosine phi, and du is negative sine phi d phi. Notice we don't have a negative sign. Pardon the pun. So we're going to multiply the inside by -1 and the outside by -1. And now we can convert, because this negative sine phi d phi, that's our du, right? And then 64 pi over 3 cosine squared phi, the cosine squared phi, that's just going to be u squared. So we end up with negative 64 pi over 3 u squared du. Integrate that and we get negative 64 pi over 3 u cubed over 3, negative 64 pi u cubed over 9 when you combine the 3's. Okay, so substitute in cosine phi for u, we end up with negative 64 pi cosine cubed phi over 9, and that's as phi goes from 0 to pi over 2. So plug in pi over 2, this is what we get. Plug in 0, this is what we get. Should include that over there. But cosine pi over 2 is just 0, so this stuff is just nothing. So we end up with a minus, which is a plus. 64 pi cosine cubed 0 over 9. Cosine 0 is 1, so we end up with 64 pi over 9. We've seen that we should switch a triple integral from rectangular cylindrical coordinates if the region in the xy plane we're integrating over is a circle or part of a circle, or the integrand has x squared plus y squared under a square root sign, like square root of x squared plus y squared, or square root of 9 minus x squared minus y squared. But if the solid we're integrating over is a sphere or part of a sphere, like we saw in this problem, then we should switch to spherical coordinates.